of our acids and bases. And this is important when we are going to study our the drugs, their particularly the ionization of the drugs. It is also related to the, of course, the pH, the pKa, and the ion trapping or the solubility of our drugs in different cellular compartments or tissue compartments. So we are going now to continue our discussion. So kahapon, we stopped on the Bronsted-Lowry definition of acids and bases. So basically, when we say an acid, according to the Bronsted-Lowry definition, a Bl acid or a Bronsted-Lowry acid is a proton donor. So meaning that when this particular acid will be placed in water or will be mixed in water, it will produce the hydrogen ions. So it will increase the concentration of the hydrogen ions. Or it will donate, it is a proton donor, it will donate its hydrogen ion or H+. So Bronsted-Lowry base is a substance that will accept the proton coming from an acid. So in this case, we have here an example of an acid-base reaction of an acid and a base. So yesterday, we defined or we identified HCl. So HCl as an acid and water as a base. So when we are going to mix this together, what will happen is the acid here, or HCl, will lose its hydrogen or its H+, and it will donate its H+ to water. So water now will become hydronium ion or H3O+. Our HCl here will now become chloride ion or Cl-. So the charge here becomes negative because our HCl loses an H+. So H+ is a proton ion. While for our hydronium here, the charge becomes positive because the hydronium ion gains, it gains a proton from water. So HCl here is our acid. Water here is our base. It is the base because it accepts hydrogen ion coming from the HCl. So this one here, the hydronium ion, is our conjugate acid, while the Cl- is our conjugate base. So our HCl, which is an acid, forms a conjugate base, and our water here, which is which is a base, will form a conjugate acid. So therefore, to form the conjugate base of an acid, we just need to take away or remove a hydrogen ion from that parent molecule. So in this case, we have HCl, and we remove a hydrogen ion to form our conjugate base. So in the case of water, it is a base, and it will form a conjugate acid. So to form a conjugate acid from a base, you just need to add a hydrogen ion coming from a proton donor or an acid. So it will become H3O+. So for a base, a base is a proton acceptor. So in this case, we have ammonia. Ammonia and water will form ammonium or NH4+, and hydroxide ion or OH-. So our ammonia here is our base, because it is the one that will accept a proton coming from water. So water will lose its H plus, and it will move to NH3 to form NH4 plus. So the sign here increases by 1 because it gains proton. For our water, water is an acid in this case. So water loses hydrogen ion, no, it donates it to the ammonia to become hydroxide ion, and the charge here becomes negative, because this is a base and it loses a hydrogen ion. So for a base or NH3 will form NH4. NH4 is a conjugate acid. So to form a conjugate acid from a base, you just need to add a hydrogen ion to that parent compound. So water here is an acid and it becomes a conjugate base. To form a conjugate base from an acid, so you just need to remove a hydrogen ion coming from the parent compound. So in solution, our water here will exist as a hydrated proton. That hydrated proton is also referred to as the H3O plus or hydronium ion. So it is the hydrogen ion that is present in water. So that is the hydronium ion. So the hydronium ion is a hydrated proton. When water accepts a proton from an acid, the product is a hydronium ion. So H2O plus H plus now coming from water is equal to H3O plus. So this is the formula of our hydronium ion. We have different acids according to the number of hydrogen atom that it can donate. So for those acids that can donate one hydrogen atom, they are called as monoprotic acids. So for example, we have here our nitric acid. So this is a monoprotic acid because it has one hydrogen atom in it. We also have the HF or the hydrofluoric acid. So it also has one. Hydrochloric acid or HCl is one also, and we have the acetic acid. So going back to this, take note that in this acid-base reaction, we have here a double line that indicates the equilibrium, meaning that this process is reversible since our ammonia is a weak base. In the case of hydrochloric acid, so the reaction is geared towards the right because this compound here will yield its conjugate base and its conjugate acid. So the dissociation of this particular compound is complete in the presence of this acid. HCl is an example of a strong acid. So for the polyprotic acid, so this is another type of acid. The compounds having more than one hydrogen ion to donate. So an example of this is our sulfuric acid. So it has two hydrogen ions that it can donate. So that is specifically called as diprotic acid. For the H3PO4 or the phosphoric acid, it has three. For the carbonic acid, it has two. So it is a diprotic acid. So these polyprotic acids have more than one ionizable hydrogen. That does not, having more than one ionizable hydrogen does not mean a stronger acid. So the strength of an acid will not depend on the number of its hydrogen atom. We also have those acids that will exist or that can act as both an acid and a base. And they are known as amphoteric acids or amphoteric acids. An example of this amphoteric acid is water. So water can serve as a base and an acid. So for our earlier example, we have here an acid-base reaction where water serves as a base. So of course that will happen in when it will partner with an acid. So for example, our HCl is an acid, and when it will be mixed with water, so water will act as a base. It is a base now because it will accept the hydrogen ion coming from HCl. For the reaction of ammonia in water, water will serve as an acid because water will lose, no, it will lose a hydrogen ion and it will donate it to ammonia to form ammonium. We also have, another example here. Uh, we have the H2PO4 or the phosphoric acid. And of course, this is an acid now. And when it will combine with water, so water will serve as a base. Water will accept one hydrogen ion coming from H2PO4 to form hydronium ion. So this one here is our conjugate acid, and this one here is our conjugate base. Now again, to form a conjugate acid from a base, you just need to add hydrogen ion. So this has positive sign because it is a base, it is an acid, and this has negative sign because it is a base. So this is the conjugate base of our H2PO4, and it loses a hydrogen ion and it donates it to water. In another example is between this reaction, so water can serve also as an acid. It will donate its hydrogen ion to phosphoric acid to form hydroxide ion. So in this case, the water, which is an acid, will form a conjugate base. Now it has a negative charge. It loses one proton. And our base here, phosphoric acid, will form H3PO4, which is the conjugate H3PO4, which is the conjugate acid of our base. So these are partners. So mag-partner ito sila. Our base here will always form a conjugate acid. Our acid here will always form a conjugate base. So this is the polyprotic acids and bases. Now examples of our polyprotic acids and bases. So the other name of amphoteric acids is amphiprotic form or amphiprotic acid. So they can act as an acid or a base. For example, we have here our hydrogen sulfide ion. So hydrogen sulfide ion can act as a base, and it can also act as an acid. So when we are going, for example, to remove the hydrogen ion of this hydrogen sulfide, so it will form a base. It will form a sulfide ion. And if we are going to add hydrogen ion to our hydrogen sulfide, it will form a hydrosulfuric acid or H2S. And that is a base. Now the same is true for these compounds. We have the dihydrogen phosphate, our bicarbonate, and our hydrogen oxalate. So they are polyprotic acids. Again, because they have more than one hydrogen ion that they can donate. So this is another illustration of our acid-base reaction according to the Bronsted-Lowry acid and base. So in this example, the water will act as a hydrogen acceptor when acids are aqueous, and this gives rise to a second definition for acids. So in this case, again, we have here our water, and it will form the hydronium ion. to form no, the conjugate base of our acid. So we have here another example of a reaction of an acid base wherein water act and will act as a base. So in this case, we have here our NHNO2. So this is an acid or a Bronsted-Lowry acid. When it will be combined with water, so this compound here will act as an acid. It will donate its hydrogen ion to water to form H3O. So this hydronium ion is the conjugate acid of water, and this one here is the conjugate base of HNO2. Okay. So in this example, now our water here serve as a base, meaning that it will accept uh, the hydrogen coming from our acid. So our base here will serve as an H plus receiver, and our HNO2 will serve as an H plus donor. So another example here is water serving as an acid. So as an acid, so it will donate its hydrogen ion to ammonia. So it will serve as H plus donor, and ammonia will serve as the base. So it will accept the H plus, so it will serve as an H plus receiver. So this reaction always come in pairs. So wherever there is a Bl acid, there is also a Bl base. They come in pairs. Wherever there is a Bl base, there is also a Bl acid. So the HNO2 here serve as our Bl acid. And our water here serve as our Bl base. Our ammonia is our Bl base, and our water here serve as our Bl acid. So we have identified earlier that when a Bl acid and a Bl base comes together, a Bronsted-Lowry acid and a Bronsted-Lowry base comes together, so they will form the respective conjugate acids and base. So how do we define a conjugate base? So a conjugate base is the remainder of the original acid after it donates its hydrogen ion. The remainder of the original acid after it donates its hydrogen ion. And a conjugate acid is the particle formed when the original base gains a hydrogen ion. So a conjugate acid-base pair is related by the loss or gain of a single hydrogen ion. So for example, we have here our carbonic acid, HCO3, and we have here our water. So when they will be combined together, they will form hydroxide ion and H2CO3. So our carbonic acid here is a base, no, since our HCO3 here will serve as a base. And because it will serve as a base, no, because no, it will accept the hydrogen ion coming from our acid, which is the water. So water here loses its H plus and it donates it to our HCO3 minus. So our HCO3 will form H2CO3, and this is our conjugate acid. Our water here, which is a base, now because it donates H plus to HCO3, or rather an acid, no, because it donates H plus to our HCO3, it will form a conjugate base. So a conjugate base, no, is formed, no, after our parent compound loses its hydrogen ion. The conjugate acid is formed after our base accepts the proton or gains a proton. So they always come in pairs, or base always produces the conjugate acid. Our acid always produces a conjugate base. So this is our conjugate pair 1 and our conjugate pair 2. So this is an example of the acid-base reactions and their conjugate acid pairs. So for example, an example of this is our HCl. HCl plus water is equal to chloride ion plus hydronium ion. So an acid donates its H plus into water. Water is a base because it receives the H plus. Water will now form hydronium ion or H3O plus, no, because it gains a proton. And Cl minus is produced after our HCl loses a proton. So this is our conjugate base. This is our conjugate acid. So itong base 2 and acid 2 here are partners. No, they are pairs. They are conjugate pairs. The acid 1 and base 1 are conjugate pairs. So for the nitric acid will combine with water. Water will lose, no, water will rather, it will accept a H plus, no, coming from the nitric acid, no, to form hydronium ion, and HNO3, nitric acid loses an H plus, no, to form NO3 minus. So our NO3 is the conjugate base of our nitric acid, and the hydronium ion is the conjugate acid of our water, which is a base. So the term conjugate comes from the Latin word conjugare, meaning to join together. So the same example here. So for ammonia again will serve as a base. Water will serve as an acid, so it will accept a hydrogen ion coming from water to form ammonium, and hydroxide ion.
Hey guys, in this new video.
So going back, no, to our pH scale, so when we are going to, no, to examine the pH scale, so the pH is usually interpreted, no, from number 1 to 14. And our pH 7 here represents the neutral pH. Below 7 or 6 to 1 is an acidic, and 8 to 14 is 8 to 14 is alkaline or basic. So in this case, now for 1 to 3 here, this represents the pH that is a strong acid. So when a substance, for example, or when an acid has a pH of 1 to 3, it is considered as a strong acid. When it has a pH of about 4 to 6, it is considered as a weak acid. Or alkaline no solution or alkaline substances, when it has a pH of 8 to 10, no, it is a weak alkali, or 8 to 11, and beyond that, it is considered to be a strong alkali. So the higher the pH of an alkaline solution, so it is stronger, and for an acid solution, the lower the pH, the stronger the acid. Paano nga natin madidistinguish yung isang compound when it is a weak or a strong acid? Aside from the pH, so later we'll know that how are we going to distinguish the two types of acid, whether it is a strong or a weak acid. So this is another scale showing the pH scale from 0 to 14. So that represents the pH of a solution. So we have here different types of solution with their respective pH. So for example, the gastric juice has a pH between 1 and 2, so it is very acidic. For saliva, the pH of saliva is between 6 and 7. For household bleach, its pH is between 12 and 13, so it is more basic, not to the basic side. We also have here the concentration of our H plus ions, the concentration of our hydroxide ion, and our POH. So our POH. So our pH here. So for example, when a substance has a pH of 7, it means that it has times 10 raised to the negative 7 concentration of hydrogen ion. So when we are going to expound that into a whole number, so magiging 0.000000001. So ganun ka liit yung number of hydrogen ions in a solution. That is why scientists have devised the logarithm. Ito yung logarithm in order to express the pH of a substance in a whole number. So this should be negative, but to do away with the negative sign, so it reverses the sign to positive sign. So 7. For a pH of 1, the concentration of the hydrogen ion is about times 10 raised to the negative 1. So therefore, when you are going to move from 0 to 1, the concentration of hydrogen ion will decrease. When you are going to move from 14, pH 14 to pH 0, the concentration of the hydrogen ion will increase. So in this diagram, so we have here our hydrogen ion. So when the hydrogen ion is greater than 10 minus 10 to the negative 7 moles. When it is greater than 10 to the negative 7 moles, the pH would be less than 7. And the solution will be acidic. So in this case, this 10 to the negative 7 here represents the pH 7. So those numbers greater than this, dito sa baba, this represents the acidic, acidic side. For when the hydrogen ion is less than 10 to the negative 7 moles, the pH is usually greater than 7. So the solution is basic. So towards the upper side of the scale, the concentration of the hydrogen ion is less than 10 to the negative 7, or less than the concentration at a pH of 7. So these are basic. When the concentration of the hydrogen ion is equal to 10 to the negative 7 moles, so the pH will be equal to 7. And the pH is neutral. So the larger the hydrogen ion concentration, the smaller the pH, and the stronger is the acid. So this one here is the strongest acid, the pH of 1 or 0. The smaller the pH, the stronger will be the acid, and the larger is the H plus concentration. Dito naman sa sa OH, dito naman sa ating basic side. So we have here the same lang pero baliktad lang siya, Saan yung ating pH? So our pH here at a pH of 1 and at a pOH of 13. So this is the concentration of our hydroxide ion in moles. At a pH of 13 and at a pOH of 1, this is the concentration of our hydroxide ion. So when we are measuring yung alkalinity of a solution based on the hydroxide ion, so this scale can be used. Yung hydroxide ion. So a pOH of 1 indicates that there is a greater number of hydroxide ion as compared to a pOH of 7. So this is another diagram showing the pH of a basic solution, neutral solution, and an acidic solution. And this is the number of the concentration of the H plus or the hydronium ion and the hydroxide ion. And this refers to the pOH. So for example, at an acidic pH of 0, this is the concentration of our acid. At a pH of 7, which is the neutral pH, so this is the concentration of our hydronium ion or our H plus. So 10 to the negative 7. When basic naman, 14, this is the concentration of our hydronium ion. So the lower the pH, the higher is the concentration of H plus. So each pH unit is 10 times as large as the previous one. A change of 2 pH unit means 100 times more basic or acidic. Okay. So pH can also be defined as the negative log or negative logarithm to the base 10 of the molar hydrogen ion concentration in an aqueous solution. So the negative log here represents the negative logarithm and it is expressed at the base of 10. And the H plus here represents the concentration in moles of the hydrogen ion. So 10 here means that the concentration is being expressed at the base of 10. So for example, when we are going to use that formula to compute for the pH of a base, which is usually expressed as a concentration of the hydroxide ion, so we can use this formula for a base. So this is our pH scale, and this represents the number whereby the pH will be neutral, strongly acidic, weakly acidic, and alkali. So for this example, the pH 1 to 3 represents a strongly acidic solution. pH 4 to 6 is weakly acidic. 8 to 10 is weakly alkali, and 11 to 14 is strongly alkali. So again, the greater the pH number, the stronger will be a basic solution. The lower the pH, the stronger is the acid. The lower the pH, the more hydrogen ions will be present in an acidic solution. The higher the pH, the more hydroxide ions will be present in the alkaline solution. So how do we differentiate a strong acid from a weak acid or bases? So earlier, on the concept of the pH partition hypothesis, we said that most of the drugs that we are using are weak acids and weak bases. But we also have those substances that are considered to be strong acid and strong bases. So strong acids or bases dissociate completely, while weaker acids and bases only partially dissociate when they will be subjected in an aqueous solution. So for example, in this example, when we are going to put or place a strong acid in an aqueous solution or in water, the strong acid will completely dissociate when it will be put in water. So the molecules of our acid will completely dissociate in water. For a weak acid, when we are going to put a weak acid in a solution, so the components of that weak acid will not dissociate completely to each other. So in this case, some of the components of the weak acid dissociate, but most of these are still attached in the solution. Majority are still in the undissociated form. So therefore, for an acid to be considered as a strong acid, when it will be placed in a solution, so it should completely dissociate. When it will not dissociate completely, that acid will be considered as a weak acid. So strong acids, they have 100% dissociation into ions when placed in water. So an example of these are HCl or hydrochloric acid, HNO3, and H2SO4. For bases, examples of strong bases are in NaOH or sodium hydroxide and potassium hydroxide. For weak acids or bases, they have partial dissociation, and both ions and molecules are not dissociated completely. Example of a weak acid is um, this one, acetic acid, and also NH3 is an example of a weak base. So for us to determine whether an acid is a weak acid or a weak acid or a strong acid. The same is for the base. No, so that particular substance should dissociate in solution. So for example, when an example of a strong acid is it's HCl, hydrochloric acid. So when we are going to put that in a solution, so our HCl will completely dissociate, to form our chloride ion and our H plus. So assuming that this is the HCl, so as you can notice here, the hydrogen ions are completely dissociated from its corresponding uh, ion. While for a weak acid or a weak base, so majority of the components, of the compound are undissociated in the aqueous solution. So for a strong acid, example is the HCl. It will completely dissociate into its component form. In water, we have the H plus and the chloride ion. So when it will be placed in water, of course, this will be a hydronium ion, and this will be the chloride ion. So this will serve as our conjugate base. So take note of the arrow here. So this is a yield symbol, meaning that the reaction is complete and the compound completely dissociates in solution. For a weak acid, acetic acid, so that is a weak acid, when it will be placed in solution, it will form this compound here. It's CH3, COO, and uh, hydrogen ion. Hydrogen ion. So the arrow here represents this is an equilibrium symbol that signifies that this particular acid will not completely dissociate in solution, so that it will only produce smaller amount of hydrogen ion in a solution. While for a strong acid, it will yield greater amounts of hydrogen ion in a solution. So we also have here the ionization of our acids and bases. We have here our strong acid, and we have here our weak acid. For strong acids, now they will yield hydrogen ion in a solution, and the reaction is more to the left, and there is a complete dissociation of our hydrogen ion. For a weak acid, so there will be more in terms of the ionization, so it will produce lesser amounts of hydrogen ions. For our strong base, so this is the reaction of our strong base. It will completely dissociate from its component parts. Now, so an example of a strong base is the sodium hydroxide. So we have here our yield symbol that signifies that the reaction is completely dissociated. For the weak base, ammonia is a weak base. So when it will be placed in the solution, it will only produce smaller amounts of hydroxide ion. So we have here our symbol here that is the equilibrium sign, meaning that the reaction is reversible. Because no, the dissociation of our NH3 to its component part is incomplete. Okay, so the same naman ito. So for a strong acid, its example of our strong acid is our HCl, and example of our weak acid is the acetic acid, no, which is the main component of vinegar. So when we are going to place hydrochloric acid in water, so this combination will yield lots of hydronium ion, meaning lots of H plus. And we are going to place an acetic acid to water. This will yield a little amount of H plus. So we also have here, another important function of our uh, hydrogen ion, aside from its role in the pH. So it will also be very important in maintaining the function of certain enzymes. So most of the enzymes are very sensitive to the effects of the H plus ions. So an example of these enzymes are the enzymes that are produced in the GIT. We have, for example, the amylase, the catalase. They are very sensitive to the concentration of the H plus ions in the solution. So for example, the activity in the shape of the enzyme is also affected by pH. So it is said that enzymes prefer to work at an optimum pH. And so for example, there are only certain pH wherein a particular enzyme will function or will have its optimum activity. So for example, in the case of amylase, it will only be working optimally at a pH of 7. So the pH of the environment is one of the major factor that will affect the ionization of our drugs or ionization of a certain substance. So for an acidic environment, when we say acidic environment, that refers to an environment where there are many free hydrogen ions. For the basic environment, there are only few available H plus ions. So a drug can exist as a ratio of the ionized molecule to an ionized molecule. So the ionized form of the drug or the ionized molecule are those form of the drug that are hydrophilic or charged. The non-ionized are those that are lipophilic or uncharged. So we have here a ratio of our ionized to an ionized form of a weak acidic drug. So an example of a weak acid drug is the NSAID, the non-steroidal anti-inflammatory drug, which is that we are using, which is aspirin. So when we are going to place our aspirin in a solution with varying pH, the concentration or the proportion of its ionized to an ionized form will also vary. Now, for example, at a pH of 1, when we are going to place aspirin in a pH of 1, the ratio of its ionized to an ionized form is equal to 1 is to 100. So there are more an ionized form compared to the ionized form. At a ratio or at a pH of 8, there are more ionized form of aspirin compared to its unionized form. So what does this imply? Anong ibig sabihin nito? When it comes to the absorption of our aspirin. So saan nga natin ginagamit yung aspirin na drug? Where do we use aspirin? Aspirin.
To relieve pain, Doc.
Okay, to relieve pain, no, because it is an anti-inflammatory drug. To reduce fever, no, because it is an antipyretic. Ano pa? Ano pa yung gamit niya? Aspirin. Ano pa yung gamit ng aspirin? So it is used to as a pain reliever. Ano pa yun?
Reduce the risk of heart attack po, Doc, and blood problems, blood flow problems.
Okay, so it will also reduce now yung heart attack. Kaya ginagamit siya sa mga may ano, no, high blood pressure. Okay, so aspirin, no, NSAID siya. It is also known as acetylsalicylic acid. So it is an acidic drug. It is a weak acid. Weak acid siya. Weak acid. So it is a weak acid, no, and it tends to ionize in an aqueous medium at high pH. So, ano yun? Aspirin tends to be ionized at a higher pH. So at a pH of 1, the proportion of the unionized form of the aspirin is greater than its ionized form. So, what is the implication of this on the absorption of our aspirin? Ano yung relation niya sa absorption ng aspirin?
Kung the more na unionized form po siya, sir, is the more siya ma-absorb.
Okay, so tama yun, no? So when there is a greater proportion or greater number of our when there is a greater number or number of our ionized form, so the drug na will be more absorbed as compared to greater yung kanyang ionized form, because again, based on the concept of the pH partition hypothesis, the unionized form of the drug is the form of the drug that will be favored for diffusion. So yun siya yung form ng drug that is lipophilic or lipid soluble. So in this case, at a pH of 1, no, so there are more unionized than ionized. How about at the pH of 7? So there are more ionized than unionized. So therefore, for aspirin, when we are going to change the pH towards the basic side, the proportion of the ionized form of the drug will increase relative to its unionized form. So that is not favorable for its absorption because, again, a drug can only be absorbed in its unionized form. How about at a pH of 3? Ano itong 1:1? What is the significance of this? Ano yung significance ng pH of 3 sa aspirin? Ano yung implication ng pH of 3? pH 3 sa aspirin. Anyone? So at a pH of 3, anong nangyari sa ating aspirin? At a pH of 3. The proportion of our ionized to unionized form is equal to 1. And this is known as the
pKa po.
Okay. This is known as the pKa of the drug. Now, at this particular pH, the proportion of our ionized and unionized form is equal to 1. So when we are going to decrease the pH to the acidic side by 1, there is also a tenfold increase in the proportion of the unionized form of aspirin. When we are going to increase the pH by 1, there is a tenfold increase in the ionized form of the drug. So when we are going to increase our pH by, for example, 3, there would be 1,000 times or 1,000 fold that the proportion of our ionized to an ionized form will be increased. No, so 1,000 times. Pag i-decrease naman natin siya by 3, so for example, from 4 to 1, so that is 3, no, 3 steps. So in-increase ngayon yung ating unionized form by 10,000. 1,000 naman yung unionized. At yung ionized naman will also decrease by 1,000 fold. So yun. So therefore, yung ating aspirin will be more absorbed in a much lower pH, no, as compared to mas ma-absorb na siya sa acidic environment. Okay, we also have here, no, a comparison of our aspirin, our sulfa drug, and our lidocaine. So aspirin here has a pKa of 3, meaning that at this pH, the concentration of the ionized and ionized is equal to 1. For sulfa-dimetoxin, so sulfa-dimetoxin is also an acidic drug. It has a pKa of 6. So at this pH, the proportion of the ionized to unionized form is equal to 1. When we are going to decrease the pH, we are also going to increase the proportion of the non-ionized form. When we are going to increase the pH, we are going to increase the proportion of the ionized form. Lidocaine is lidocaine is a weak base. So lidocaine is a weak base, so it has this is a basic drug, no? It has a pKa of 1:1. So increasing, no, the pH will favor the absorption of this drug, no, because it will increase the proportion of the unionized form, no, because it is the unionized form that will be absorbed. So the pKa is the pH level at which the ratio of the ionized and unionized form is the same or equal to 1. So it is constant for an acid or a base. Example, the aspirin has a pKa of 3.5. So the pKa value in chemistry is also defined as the negative base 10 logarithm of the acid dissociation constant, or the Ka of a solution. So this is the formula for computing the pKa. This is equal to negative log 10 of the Ka. So the smaller the pKa value, the stronger is the acid. So for example, okay, later yung example. So we have here comparison of our, so this is our pKa here. So the lower the value of our pKa, the stronger will be the acid. The higher, the weaker is the acid. So the pKa also is used to identify or to determine the strength of our acids. It determines the strength of the acids. So for example, when we are going to, for example, compare these three types of acids, so the acid having the lowest pKa will be considered to be the strongest. So at this point, this acid, because it has a pKa of 3.74, it is considered to be the strongest acid. So the importance of this is that the importance of determining the strength of the acid is that all acid-base reactions proceed from the stronger acid and base to the weaker acid and base. So for example, in this case, our HCl here is considered to be a strong acid, so that this type of reaction will always proceed from left to right, from the stronger acid to the weaker acid. The same is true for bases. So the reaction will always proceed from the stronger to the weaker base. So these are examples of the common acids, the pKa values of the common acids. So for example, we have here acetic acid has a pKa of 4.76. When we are going to compare that with sulfuric acid, and sulfuric acid has a pKa of -2. So the lower the pKa value, the stronger is the acid. So going back to our examples here, so lidocaine has a pKa of 3. It's a basic drug. Sulfadimethoxine is a weak acid. It has a pKa of 6, and aspirin is a weak acid with a pKa of 3.5. So the lower the pKa, the stronger is the acid. So aspirin is much stronger than sulfadimethoxine. So the pKa value of the drug or the compound will not tell whether the species in question is acidic or basic, because there are certain acidic compounds that are certain acidic compounds with a pKa value of, for example, 9.9. An example of this is phenol. So phenol is a weak acid, but it has a pKa value of 9. So this is the difference between the pKa and pH. So when we are going to compare the two, so a pKa would indicate whether an acid is strong acid or weak acid. So basically, pKa will identify the strength of the acid. For pH, it will indicate whether a system is acidic or basic. Another difference is for pKa, it will depend on the concentration of the acid, the conjugate base, and the H plus ions. while for the pH, it will solely depend on the concentration of the H plus ions. So if the pKa of the acid is high, so it is considered to be a weak acid. If it is low, it is considered to be a strong acid. If the pH is high, no, the system is alkaline. If the pH is low, the system is acidic. So these are the difference now between our pKa and pH. So we have here examples of the different type of acids, strong acids and weak acid. So again, no, for pKa value, the higher the pKa, no, the weaker is the acid. So for example, thiopental, no, has a pKa of 7.5. So it is a weaker acid, no, compared to, for example, penicillin, no, with a pKa of 2.8. For bases, the higher the pKa value, the stronger is the base. Example, lidocaine uh, is a strong acid. No, it is a strong base. It has a pKa of 7.9. Diazepam is a weak base. It has a pKa value of 3.10. So these are the importance of the environmental pH, and the drug pKa. So the degree of ionization or polarity will depend on the pKa value of the drug and the pH of the body fluid. So again, the pKa is a characteristic or property of our drug, and it is considered to be constant. The pKa value, so if the pKa of a drug is equal to the pH of the media, so then 50% of the drug is in the ionized form and 50% is on the unionized form. So only the unionized form of the drug can partition across biological membrane, providing the unionized form is lipophilic. So the ionized form will tend to be more water soluble. This is required for drug administration and distribution in plasma. So for a drug to be distributed in the body, and for it to be able to be transported in the blood, it needs to be ionized, or it needs to be more water soluble. For a drug to pass through a different biological membrane, it needs to be an ionized, or it needs to be a lipophilic. So as a summary, high pKa means that the acidic drug is predominantly unionized, and this is a bad proton donor and a weak acid. A low pKa value for an acid means that the acid is predominantly ionized. So pag mas higher ang pKa, mag-lower ang pKa value, the drug is predominantly ionized, and this is a good proton donor, and it is a strong acid. For a pKa, when the pH is less than the pKa by 2 units, the acid is considered to be 99% unionized. When the pH of the environment is greater than the pKa by 2 units, the acid or the drug, or the acidic drug, is considered to be 99% ionized. So therefore, when we aim for the proper absorption of our drug, we need to decrease the pH in order for that particular acidic drug to be absorbed, in the environment, or to the acidic environment. For bases, a high pKa means that the species is predominantly ionized, and this is a good proton acceptor, and it is a strong base. A low pKa means that the species is unionized. It is a bad proton acceptor, and it is a weak base. So again, a basic drug that has a low pKa is also considered to be a weak base and a bad proton donor because, again, when we say a weak base, this type of drug will not completely dissociate in solution. So it will only produce a small amount of hydroxide ion. That will be also a bad proton acceptor. For an acidic drug, a low pKa value would also mean that it is a strong acid, and it is a good proton donor because a strong acid will always dissociate completely in a solution, so it will provide more H plus ions in the solution. So for the ion trapping is a phenomenon whereby drugs are kept in an environment of altered pH by the change in equilibrium brought about by the change in pH. So we have here a diagram showing two tissue compartments. One tissue compartment has a pH of 5 and one tissue compartment has a pH of 7. So the pH of the environment can influence the distribution or the steady state distribution of a particular drug. So in this case, we have here our example is a weakly acidic drug with a pKa value of 6. So since it has a pKa value of 6, at the pH of 6, now the proportion of the ionized to the unionized form will be equal to 1. So that when we are going to decrease the pH by 5, so halimbawa, when we are going to place the drug at a pH of 5, so automatic na ngayon na yung unionized form of the drug will be equal to 10. Because again, di ba, mag-i-increase yung unionized form of the drug when you are going to increase or decrease rather the pH by 1 for an acidic drug. So for a weak acid, when we are going to place that on a pH of 5, which is acidic, the drug will be the drug will favor an ionized form relative to the ionized form. So in this case, it will have 10 moles of that particular drug and only 1 mole of the ionized drug, for a total of 11 moles. So this an ionized form of the drug will be able to cross the lipid bilayer. So for example, when this tissue compartment has a pH of 7, so this is towards the basic side. So this will favor the ionization of our weak acid. So the weak acid will be more ionized relative to its unionized form, so that this particular drug will be trapped in this environment. So it cannot go back to its origin because it is trapped in this particular tissue compartment. So we have different tissue compartments in the body. So for example, the plasma has a pH of 7.35 and 7.45. The stomach in humans has a pH of 1 to 3. So that is very acidic. Or the duodenum, no, it has a pH of 4 to 8. And of course, that will depend on the diet. The pH of these tissue compartments will influence the ionization of our drugs. So absorption after ingestion is affected by pH gradient between the drug and the absorbing surface. So for example, in the stomach, which is highly acidic, acidic drugs are absorbed while basic drugs tend to accumulate. In the intestine, which is only slightly acidic, basic drugs are better absorbed than acidic drugs. So this is the effect of the ionization on the drug absorption. So for example, for those drugs that are, so meron tayo dito na one here. This is an ionized drug that is placed in the stomach with a pH of 2. So these ionized drugs cannot easily pass through the membrane, while the non-ionized drugs can easily pass through the membrane. So for example, this drug here at number 2, it will pass through the, so this is, since this is an unionized drug, so it is a weak acid. Now, since it is placed in the stomach, which is also an acidic environment, so this acidic drug can pass through the cell membrane, and this drug will be ionized in the blood because the blood has a pH of 7.4. In the intestine, the non-ionized form of the drug will be ionized, and the ionized form of the drug cannot pass through the cell membrane. So we also have here an example of an acidic drug. So an acidic drug with a pKa value of 4. So the ionization state will be as follows. So when we are going to place the acidic drug in the stomach, so stomach is acidic, the acidic drug will be ionized. It can pass through the cell membrane, and it can be absorbed in the body. For those drugs, for this drug, when it will reach the intestine, so the drug will be ionized so that it cannot be absorbed in the body. For basic drugs, the ionization state will be as follows. So when we are going to place a basic drug in the intestine, it will be ionized. It will be absorbed in the body. So when the basic drug is placed in the stomach, it will be ionized. Rather, it will be ionized, and it will not be absorbed in the body. So this is another example of the diffusion of a weak acid. So the same principle. So for example, we have here our stomach with a pH of 2, and for example, the urine with a pH of 8, and the plasma with a pH of 7.4. So for example, a weak acid will form an ionized form of a weak acid will predominate in the stomach. Its ionized form will be equal to 0. So 100, this will be the the concentration of our ionized form of the drug, 100 relative to 0. So the unionized form of the weak acid will predominate in the stomach. So this unionized form can be absorbed. It can be absorbed in the bloodstream. So when it reaches the bloodstream or in the blood or in the plasma, plasma has a somewhat basic pH, so that our weak acid will be ionized. So the ionized form will not be able to pass through our membrane. The unionized form will be able to pass through our membrane and reach the urine. So in the urine, since the urine has a basic pH, the ionized form of the weak acid drug will predominate. So the ionized form will not be able to go back or will not be able to pass through our membrane. So it will not be reabsorbed in the body, so that most of it will be eliminated or excreted in the body through the urine. For a weak base with a pKa of 7, when we are going to place the weak base in the stomach with a pH of 2, so the ionized form of the drug will predominate, so it will not be absorbed in the bloodstream. So when the weak base is present in the plasma, the unionized form of the drug will predominate because again they have the same pH, basic pH. So the unionized form of the drug will predominate, and this unionized form will be the one to pass through the membrane, and it will reach the urine. So for example, our urine here is acidic. So in an acidic urine, our base will be ionized. So the ionized form of our drug, weak base drug, will be eliminated in the body. It will be trapped in the urine, and it cannot be reabsorbed back into the body. So this is another example of ion trapping. And our example here is a weakly acidic drug with a pKa value of 2.4. And the stomach has a pH of 1.4, that is acidic. And the plasma with a pH of 7.4, and that is towards now the basic side. So in the stomach, so when we are going to place now the weakly acidic drug in the stomach with a very acidic pH, so the an ionized form of the drug will predominate relative to the ionized form. So this unionized form will be the one to pass through the membrane, and it will be absorbed in the circulation. So the acidic drug in the blood will be ionized. So the ratio here is 100,000 over 1. So 100,000 because the difference between 7.4 and 2.4 is equal to 5. So we add here 5 zeros in order to get the concentration of our ionized to unionized form. So 100,000 is to 1, meaning that the weakly acidic drug will be ionized in a basic environment. So this ionized form will be trapped in this compartment, meaning that this drug will be staying, it will be staying in the blood for a long time because it is trapped in this particular compartment. Okay, so as a summary, the unionized form of the drug will mimic the lipid. So the lipid is the unionized form of the drug will be lipid soluble, so it will mimic the lipid, and it will increase the absorption of that drug and decreasing its excretion in the body. The ionized form of the drug will mimic water, so that it is also known as the hydrophilic form. This will decrease its absorption in the blood, and it will increase its excretion in the body, for example, through the urine. When we are going to place an acidic drug in a basic solution, this will increase its excretion. And when we are going to place a basic drug in an acidic solution, this will increase its excretion and decrease its absorption. When we are going to place an acidic drug in an acidic solution, basic drug in a basic solution, so this will decrease its excretion and increase its absorption in the blood or in the body. So we will continue this next meeting. So may questions kayo sa sa ating lecture. So I will just upload this sa ating social media para mabalikan ninyo. Okay na? So we will see you next week. So good morning to everyone.
Thank you, sir.
Thank you po, sir.
Thank you, sir.
Thank you, Doc.
Hi, Mike.
What's wrong?
Wala lang. Hi, Mike.
Hello, Joy. Hello, Alana. Tapos na ka mo sa drinker.
Yes, bitch.
Amo lang to, ipakita lang kay ma'am, no? Okay lang mo siguro nga
Hindi
tikatik
ka
lang.
function. Tikatik naman din sa akin, Mike.
Pero may nilagay ka na, na drinker.
Drinker. Ay, yung kwan, kagatan ng baboy. Meron.
Oo, meron. Patingin daw pa.
Wait lang.
Revisit.
Oo. Nag-ito ka?
Oo, ganyan. Wait lang, pakita ko sa ako na. Dahil lang.
Hindi ko pa na-assemble sa akin.
Pero may ano ka na pa. Ganito, Wait lang.
Meron, may ganyan na ako.
Tapos ano ilagay mo dito pa?
Kahit ano lang. Ay, yung galon sa akin.
Galon lang.
Yeah.
Mm.
Yeah, Mike. Bye-bye.
Okay, pao.